solving trig equations. Okay, so welcome, pre-calculators and trigonometers. We are going to look at solving trig equations, and I wanted to start out with an equation that you'll never see. Okay, simple equation, simple example, let's solve it. Okay, let's say I want to get x alone. That's the idea of solving, is to isolate the variable. So I'm going to move this over here. So I get 2 times the sine of x equals square root of 3. And then I think I'll divide both sides by 2. So I can get sine of x alone. And then I'll ask myself, what x value, if I take the sine of it, what angle gives me a sine of square root of 3 over 2? And the first one that comes to my mind is 60 degrees or pi over 3. So I'm done, right? Well, I would be if I were ever asked questions like that, pretty much. The reality is you're never going to be asked a question like that. What do I mean by that? Well, you're never going to be asked a question where you're not given some guidance. You're never going to be asked to solve a trig equation without being given some guidance as to which solutions we're looking for. Here's what I mean. When I got to here, I said, oh, okay, let me think about where the sine is square root of 3 over 2. Well, sine is square root of 3 over 2 right here at 60 degrees, which is also known as pi over 3. So I said, hey, great, that's my answer. But the reality is the sine is also equal to positive pi square root of 3 over 2 over here, 60 degrees above this side, where we have another reference angle of 60. The angle is 120, or at 2 pi over 3. That also has a sine of square root of 3 over 2. So which one do I want? But wait, there's more. Not only that, but what about the angle 420 degrees? Okay, 420 degrees, I start here, I go all the way around 360, and I add 60 more degrees, and boom, there I am, and I have a sine of square root of 3 over 2. What about the angle negative 5 pi over 3? Or for that matter, what about negative 4 pi over 3? Negative 4 pi over 3, I go this way, because I'm going negative 3 pi over 3, which is 1 pi here. Go another 1 pi, negative 4 pi over 3 is right here. So yeah, that location has a sine of square root of 3 over 2. The point is there are an infinite number of angles that have a sine of square root of 3 over 2. You may remember, as you may also be hearing my dog sneeze constantly. I'm not sure what that's all about. But you may remember way back when you started trig and you started talking about reference angles. You talk about how this has a reference angle of 30 degrees, and so does 150. It has a reference angle of 30 degrees. At the same time, sorry, couldn't see that. At the same time you talked about reference angles, you also talked about coterminal angles. Coterminal angles are angles that have the same, whose terminal side is in the same place. In other words, 30 degrees is coterminal with 390 degrees. Because if I go all the way around, 360 and 30 more, I get there, 390 degrees ends up in exactly the same place. It's also coterminal with negative 330. Because if I started here and went this way, 330 degrees, I'd get to the same place. It's also, and we could keep going. We could keep adding, and since I'm in degrees, in this case, could keep adding 360 to this over and over and over again, and I'd keep ending up in the same place. Why 360? Because 360 is all the way around. So if you have a location where your angle has its terminal side, you go all the way around, either clockwise or counterclockwise, it doesn't matter, you're going to get back to that place again. So if you add or subtract 360 or 360 times 2, or 360 times 3, or 360 times 4, or 360 times 5, etc., you're going to get to another angle that has those same values. Same is true for radians. This would be pi over 6, and that would also be the same as 13 pi over 6, or the same as negative 11 pi over 6. And remember that all the way around the circle, in terms of radians, is 2 pi. So basically, instead of adding 360 and adding 360 and adding 360, or subtracting 360, subtracting 360, etc., you're adding 2 pi each time. I could find more angles that have that same terminal side by adding 2 pi. Well, 2 pi, if we're thinking of sixths, would be 12 over 6. 12 over 6 is 2. So if I add 12 to 13, 25 pi over 6 has the same terminal side. It's in the same location, so it has the same sign, the same cosine, the same everything. Add another 12. 37 pi over 6. I can keep going. 2 pi, 2 pi, 2 pi. So this is pi over 6. I can say pi over 6 has that value. Pi over 6 plus 2 pi. Pi over 6 plus 2 pi times 2. Plus 2 pi times 3. Minus 2 pi. Minus 2 pi times 2. Which would be minus 2 pi times 3, etc. All right, so basically we just need more guidance. We can't just be told solve. That's not enough. So every time you're asked to solve, you're going to get more guidance. And you have to read the problem carefully to know what you're being asked to do. Generally, you're going to see something like this. Okay, another one you might sometimes see is say find the principal value. The principal value means go to the most basic value, like for instance here, 60 degrees. And I would choose 60 because do you remember when we did inverse sine positive values we did in the first quadrant? We didn't go over here to the second quadrant. So my positive for sine is first quadrant, negative for sine is down here. So those would be principal values. But a lot of times you get one of these. Either find all solutions or find the equation or solve the equation on a specific interval. And the interval it usually says is 0 to 2 pi or 0 to 360 because that's basically one time around the unit circle. Just go, sorry, I went the wrong way. One time around the unit circle. All right, so let's do one from our review that I'm trying to do problems for my students from. This one is actually a little challenging. It's a little bit next step. But this is the first one we have that says, solve the equation on the interval 0 to 2 pi. Now, one thing to notice about this is you have a bracket on 0 and you have a parentheses on 2 pi. 0 and 2 pi are the same location. So they're basically saying that if your answer is that location, go with 0. We include that. We want to use that one. We don't want to use this. We want to go right up to 2 pi, but not actually include it. Okay, so here's the problem with this one. This is a unit circle value. I'm ready to solve it, but then I notice, oh wait, this says 2x. Okay, I can't just say, let me do inverse cosine and I'll get x. This is a double angle. So am I supposed to use a double angle formula? What am I supposed to do with this? Nope, here's what we do. We let something else stand in for this. I'm going to say u. And u is something we use a lot to stand in for something else. Particularly in calculus, you'll do a lot of this. And I'm going to solve it for that. So in other words, the cosine of u is equal to square root of 2 over 2. Well, I know there are two places between 0 and 2 pi where cosine has a value of 2 pi over 2. Right out in the middle of the first quadrant, and right over here in the middle of the fourth quadrant, which is 7 pi over 4. Okay, basically your 45-degree angles. Now, why did I use radians instead of degrees? Because the problem was using radians. Why? Do you remember when we did inverses? You sometimes on the fourth quadrant had to use negative values from the first quadrant instead of just fourth quadrant values. Why did I use fourth quadrant values? Because of this. This is saying you're doing it on the interval 0 to 2 pi. So when you get to the fourth quadrant, you're almost back around to 2 pi. So this is almost 2 pi-ville. So those are the two places that we have a positive square root of 2 over 2 for cosine. And then you go up, or then you go down. Sorry, I didn't really align. All right, so my answers would be pi over 4 and 7 pi over 4. Except here's the problem. We don't have x. We're saying u is pi over 4, or u is 7 pi over 4. So basically what we do is we solve it for just figuring out the values, and then we go back and we put what u actually stands for and finish solving. So now we say, well, u is actually 2x. So 2x is equal to pi over 4. 2x, equals 7 pi over 4. And then how do I get rid of the 2 in front of the x? I divide both sides by 2, which is the same thing as multiplying by 1/2, which I like to think of it that way since we have a fraction over here. So we have x equals pi over 8. That's one of my solutions. And same thing over here. X equals 7 pi over 8. There is my other solution. All right, so those are my two solutions. I'm only going to have two solutions because there's only two places between 0 and 2 pi that the cosine has a value of positive square root of 2 over 2. Those are my answers. If they had asked me to do it finding all solutions, I would have to do something a little different. So let's look at a problem like that. And again, if they had asked me to find all solutions, the beginning part would be pretty much the same. I would basically go to the same place with this. It's just that how I would write my answers would be different. So let's look at one like that. And the one we're going to do like that is actually a simpler one to solve. It's a lot like the first example I gave you. Okay, so there's nothing funny going on with 2 pi or 2 theta or 2x or x over 2 or anything like that. It's just plain old x. So I want to first move this. And then divide by 2. So I get sine of some angle is negative square root of 3 over 2. Negative square root of 2 over 2, sorry. Okay, so now I need to think, same idea, on the unit circle, where is the sign negative? Well, that's down because the sign is our y value. Where is it negative square root of 2 over 2? Well, right in the middle of this quadrant, right in the middle of this quadrant. This right here is negative root 2 over 2. This is negative root 2 over 2. Okay. Now, this one did not actually give me any guidance in terms of should I use degrees or radians, but given that I'm doing a review on which the other problems were the one we just did, where is it? Was asking me for radians, I'm going to go ahead and do radians. A lot of times radians is your best bet when in doubt. Okay, so here radians, that would be 5 pi over 4. And here in radians, that's 7 pi over 4. But here's the thing. Key word, very big word here, the word all. Okay, 5 pi over 4 and 7 pi over 4 are not all the solutions because of what we talked about before. Okay, if I were to go all the way around the circle in either direction and land here again, then I would have found another angle that has that exact same sine value, but it won't be 5 pi over 4 anymore. So any angle that is coterminal to 5 pi over 4, or any angle that is coterminal to 7 pi over 4, is a potential answer if we want all solutions. So here's how we describe that. Remember how I was saying if you go all the way around 360 or go 360 twice, well, I didn't keep going with this, but if you go 360 2 times or 3 times or 4 times or 5 times, it doesn't matter how many times you go all the way around, you'll land back in the same place. Same thing with radians. If I start at pi over 6 and go around 2 pi, I'm at 13 pi over 6. Go around 2 pi times 2, here. 2 pi times 3, here. If you go around the circle, all the way around the circle, which is either 360 or 2 pi, however many times, you will get to another solution. So that's how we write our answer. We say all solutions can be represented by 5 pi over 4 plus all the way around the circle, however many times you want to go. In terms of radians, all the way around the circle is 2 pi. And to say however many times you want to go, we just put an integer, or we just put a variable that stands for an integer. Okay? A lot of times we use k. Sometimes we use n. So that's kind of up to your teacher and your textbook as to whether you're using k or n. But that basically means I can go all the way around the circle as many times as I want. K could be 1 time, 2 times. I could make it go in the negative direction by having k be -3, -2, -1, -7. I will get back to another location that is exactly the same in terms of sine, cosine, and tangent, in terms of all the values, as 5 pi over 4. Okay, if we had done this in degrees, this would be, let's see, 225 is the first location. Over here we have 315. And we would say all solutions is what you want. Well, that means as many times as you want to go, 360 in either direction. That's a K. Okay, now something special about that is the all the way around is true for sine and for cosine. But if you think back to what you did and think about graphing these. Remember when we graphed sine and cosine? The period was 2 pi. It took 2 pi, it took going all the way back, all the way around to get back to where you came from. But not for tangent and not for cotangent. Tangent and cotangent repeated every 1 pi. So it turns out that if this were a tangent problem, instead of saying go all the way around k times, it would be just go pi, go halfway around k times. And instead of 360, it would be 180. Okay, so that's if it were a tangent problem. And I had answers, and I was trying to indicate that I wanted all answers. I would say plus, instead of saying plus 2 pi times k, or plus 360 times k, which is what I say for sine and cosine, and secant and cosecant, because they go with sine and cosine. For tangent or cotangent, they have a different period. They repeat every 1 pi or every 180 degrees. So I would write that differently here. All right, let's do, I think that's about it for this one. Yeah, we're going to stop here. I will do another video that has a couple more examples like this. Hope this helped. Thanks so much for watching. See you next time.